In the beginning, there was an incredibly dense and hot mass of matter. This mass is believed to have undergone a powerful explosion, the Big Bang, that started the expansion of everything we know today. From this explosion, atoms, molecules, stars, and galaxies came into existence. It laid the foundation for the universe as we see it now. For many years, this explanation satisfied scientists and aligned well with cosmic observations and mathematical models. However, more recently, new research and theories have emerged that challenge the traditional Big Bang theory. Some scientists now suggest that the universe may not have a singular beginning. Instead, it could be part of a larger, cyclical process of expansion and contraction. This idea proposes that the universe goes through endless loops, expanding, collapsing, and then starting anew. A leading voice raising questions about the Big Bang is Brian Cox, a respected physicist. He argues that something cannot come from nothing. This philosophical challenge adds a deeper layer to our scientific quest. It suggests we may be missing something fundamental about the origin of the cosmos. Adding to the intrigue is recent data from the James Webb Space Telescope, which has uncovered evidence that could contradict the Big Bang being the absolute start. Some of these discoveries include galaxies that appear too old or structured to fit within the current timeline of the Big Bang. If these galaxies really are older than the theory allows, then something else might have happened before the Big Bang. This leads us to a profound question: if the Big Bang wasn't the beginning, then what came before it? Understanding what came before the Big Bang requires pushing the limits of our current physics. Physicists have developed a strong model describing the early universe, the Big Bang theory. According to this model, the universe began about 13.8 billion years ago. In the moments after the Big Bang, the universe was extremely hot, dense, and small. It expanded rapidly, cooling down as it grew. During the first few minutes, light elements like hydrogen and helium formed, and over time, stars and galaxies emerged. At one point, all the matter in the universe was packed into a space no larger than a peach. The temperature was over a quadrillion degrees. This narrative aligns well with many observations, such as cosmic microwave background radiation, the leftover glow from the early universe. It also matches predictions about the abundance of light elements like helium and deuterium in space. Despite its success, the Big Bang theory is not complete. One key limitation is that it can't explain the very first moments of the universe. The deeper we go into these early moments, the more complex and unstable our mathematical models become. At the heart of this problem is the concept of a singularity, a point where density and temperature become infinite. This idea suggests that the universe began from an infinitely small, dense point, but this leads to mathematical absurdities. Current physics, which combines general relativity with quantum mechanics, cannot handle such conditions. To better understand these moments, scientists believe we need new theories that unify all fundamental forces, especially at high energies. This is where string theory becomes relevant. String theory aims to be a theory of everything, explaining gravity and quantum mechanics together. According to string theory, the universe's first moments may not involve a singularity but instead a more structured and continuous process. One idea from string theory is the ekpyrotic universe. This concept comes from the Greek word for conflagration, or fire. It suggests that the Big Bang was not the start, but the result of a collision between higher dimensional objects called branes. These branes exist in a larger multidimensional space, and their collision caused an explosion that looks like a Big Bang from our perspective. From this idea comes a more refined concept known as cyclic cosmology. It proposes that the universe has no beginning or end, only cycles. In this model, the universe goes through endless phases of expansion, cooling, contraction, and rebirth. Each cycle could last trillions of years, with one universe giving birth to the next. This concept isn't new. Philosophers and ancient civilizations have pondered the idea of a cyclic universe for centuries. However, string theory gives it a mathematical foundation, making it a serious topic in modern cosmology. The idea gained momentum thanks to Roger Penrose, a Nobel Prize-winning physicist. Penrose noticed an unusual mathematical similarity between the very early universe and the very distant future. According to him, both states can be considered identical under extreme conditions using a method called conformal transformation. A conformal transformation changes the scale of space and time but keeps their geometric relationships intact. Penrose's theory says that after all matter in the universe is consumed by black holes and the black holes evaporate, only photons remain. These photons fill the universe, making it cold and empty, but under the right mathematical lens, this state becomes identical to the Big Bang. In other words, the end of one universe is the beginning of another, and this process can repeat forever. What's fascinating is that Penrose believes size and time lose their meaning in these extreme states. So from one point of view, the universe is a cold void, and from another, it's about to explode into existence. This theory, called Conformal Cyclic Cosmology, CCC, allows for an infinite sequence of universes. Each universe is born from the end state of a previous one, creating an eternal, rhythmic cycle. In this framework, our universe might not be the first. There could have been countless others before ours. Each cycle might slightly differ from the last, with variations introduced by quantum events. These quantum fluctuations could leave traces in the universe we can detect today, such as patterns in the cosmic microwave background. This opens up the possibility of experimentally testing cyclic cosmology, making it not just a philosophical idea. If we find anomalies in the radiation from the early universe, they could be signals from a past cycle. Penrose and other researchers have even claimed to detect circular patterns in the CMB, though these findings remain debated. The concept of a cyclical universe offers a compelling alternative to the idea of a one-time Big Bang. It also provides answers to deeper philosophical questions, like why there is something rather than nothing. In the cyclic model, the universe didn't arise from nothing, it arose from the remains of a previous cosmos. This avoids the problem of uncaused beginnings and offers a more continuous narrative for the universe. There are a few possible versions of this idea. One is that there is no ultimate cause, the cycles simply always existed. Another is that each cycle influences the next, like a cosmic domino effect, where each universe sets up the conditions for the one that follows. A third possibility is that a single repeating universe explains itself, with the end and beginning tightly linked. All these versions attempt to provide a complete picture of reality, based solely on physics. Penrose ties these ideas to quantum mechanics, where systems can exist in multiple states until observed. He believes that random quantum events shape each new universe, creating subtle but detectable changes. These changes might be seen as irregularities in background radiation, offering a potential way to test the theory. Scientists continue to explore these ideas, designing better instruments and new methods to detect such clues. The James Webb Space Telescope, with its deep views into space, may help us learn more about the earliest galaxies. If it keeps finding galaxies that look too old for the standard Big Bang timeline, the case for alternative models will grow stronger. Theories like CCC also influence how we think about the future of the universe. Instead of ending in a cold, lifeless void, our universe might simply transition into a new cycle. That cycle would bring about new stars, galaxies, and perhaps even new versions of ourselves in some form. This continuous renewal offers a hopeful perspective, turning the end into a new beginning. Of course, many questions remain. We still don't fully understand how quantum gravity works, or how to unify it with relativity. The mathematics of these ideas is incredibly complex, and we are just beginning to develop the tools to explore them. Yet, the progress so far shows that our universe may be far more intricate than we once believed. The mystery of our origin may never be fully solved, but each step brings us closer to understanding our place in the cosmos. Whether through string theory, quantum gravity, or new discoveries yet to come, the journey of discovery continues. We are part of an ever-evolving universe, possibly one of infinite others, and the story is still unfolding. If the cyclic model is true, it may change not just science, but our entire worldview. The universe, far from a one-time event, becomes a timeless rhythm of creation and transformation. This concept challenges and inspires us, inviting us to think beyond the known and embrace the mysteries of the cosmos. Subscribe to our channel and thanks for watching.